This is Lecture 1C from Calculus 1. It's a lecture on polynomials, roots, and the power functions. Obviously, we have to start with the definition of a polynomial. Polynomials are built on monomials. A monomial is a product of a number called the coefficient and one or more variables with whole number exponents. The monomial has a degree, or sometimes I call it the order, and that is the sum of the exponents. So in a monomial, everything is multiplied together. There's no addition, there's no subtraction. For simplicity, and since this class is single variable calculus, we can limit the discussion to monomials and polynomials of a single independent variable. So here's the definition of a polynomial built on the definition of monomials. A polynomial is a sum over a set of monomials. The monomials are called the terms. The numbers multiplying the variables are again called the coefficients. And the degree or order of the polynomial is the degree of the largest monomial. Here is the general form of a polynomial, and this is a very important thing to know. Okay, so p of x meaning polynomial in x. X is the independent variable. All of the monomials are arranged, in this case, in descending order. You could also write the polynomial in ascending order. It's descending because you start with the highest value, the highest exponent on the variable, x to the n, and then just count down. X to the n minus 1. So if this was 5, n minus 1 would be 4, n minus 2 would be 3, n minus 3 would be 2, on and on, till you get down to a1 x to the 1 and a0. a0 is the constant. The coefficients are labeled with the letter a, and the subscript on the coefficient matches the power of the x that it's multiplying. So a to the n, x to the n. Right? A to the n will be a number. A to the n minus 1 is a number. It's a number multiplying x to the n minus 1. So if n was 5, this would be a sub 5, x to the 5th, plus a sub 4, x to the 4th, plus a sub 3, x cubed, and so on. The degree of this polynomial is n. This is just a general form of the polynomial. So in this case, like I was saying, if n is 5, the degree of the polynomial would be 5. Some of these coefficients can be 0, and so not all these terms might be present in a particular polynomial, but this is the general form of a polynomial. The highest order term, this x to the n, a to the n, is called the leading term. A to the n is the leading coefficient, and again a0 is the constant. The easy operations with polynomials are addition and subtraction. In the past that was called collecting similar terms. And the polynomials can be multiplied. If they're binomials, you can use the FOIL method, first, outside, inside, last, or some extension of the FOIL method so that all terms are multiplied together in the end. Okay, so why study polynomials? Well, first of all, many physical processes behave like polynomials, so that's one good reason to study them. The other very good reason is the graphs of polynomials are smooth and continuous. Polynomials, their domain is all real numbers. They're very easy to work with. And then we come to the idea of the polynomial approximation. If you have very complicated data, you can approximate it with a polynomial. So what used to be very complicated, scattered-looking data can then have a functional form that's very easy to work with. So that's called a polynomial approximation. It approximates very complicated data or a very complicated curve. And actually the approximations can be very well. You might need a lot of terms to the polynomial, but it will still be a good approximation. Before I didn't mention dividing polynomials, because when you divide polynomials you'll end up with something totally new. You end up with a rational function. So here is a pen. Okay, here's a rational function. In the numerator is a polynomial p, some function of x, and here's a polynomial in x, q of x, in the denominator. For all the other polynomials, when you have a polynomial, the domain is all real numbers. Now you have created this fraction, this ratio of polynomials. And if you remember from the previous discussion, when you've done something like this, you inherit the domains from the functions you are putting together, in this case dividing. The domains of p of x and q of x is all real numbers, so there's no problem there. There are no limitations. The limitation comes in with the q of x in the denominator. The denominator of this rational function cannot be 0. So all zeros, all roots of q of x have to be excluded from the domain. In the past, we just excluded them from the domain and wrote them in a list, but here they will have another name and a whole other value, and they will become the vertical asymptotes. The vertical asymptotes are the values of x for which q of x goes to 0. They are not part of the domain, but they have a name, and the name is vertical asymptotes, and I'll show you some in a minute. Other points of interest are the x-axis intercepts. The x-axis intercepts are the roots of p of x. When p of x is 0, the whole function is 0, assuming that value is in the domain. And the horizontal asymptotes are the value that the function takes on as x becomes very, very large, as x approaches infinity. Okay, here's a graph of this function, and there's several things to point out here. First, we had roots of the denominator when x was positive 3 and x was minus 3, and that's where the function crosses the x-axis. And we can see those points right here. They're labeled here, and they're labeled here. And you can see that the function is positive here and becomes negative. And here it becomes negative, but you can barely see it, but it's true. There's a root right there at x equals minus 3. So at those two values, the function crosses the x-axis. Right. The vertical asymptotes were the points 0, minus 2, and 8, and those were the three we kicked out of the domain. However, they appear as vertical asymptotes, and there's something to be pointed out here. So the vertical asymptote at x equals 8 is right here. Okay. There's a vertical asymptote at x equals 0. See that here? And the vertical asymptote at x equals minus 2, and that's right here along this line. All right. And the note here is this vertical line should not be here. The computer drew it. Computer graphing routines, particularly the graphing calculators, will draw a line as it tries to draw this function. So it's red. It's a red line. It goes here, and this is approaching infinity, which is why we call it a vertical asymptote. And then it starts coming in from negative infinity and makes this other curve. Okay, when the computer is drawing it, it will forget to lift the pen, so to speak, and it will draw this vertical line right down here that you're seeing here. It should not be here at all. This vertical line here shouldn't be here. But computer graphing routines draw it. It doesn't exist. It's just a artifact of the drawing routine. Over here, it decided not to draw it at x equals 0. Well, maybe it tried to, and the axis was strong enough to kind of mask the red line there. But here again, at x equals minus 2, the function, where's my marker? The computer graphing routine did draw this vertical line. You just got to be aware that it will do those sort of things. What does the word asymptote means? You can think of it as a guideline. It gets the function gets closer and closer to this guideline. It could even cross it and oscillate down onto it. It approaches this guide, but it never really gets there. Well, sometimes it gets there, but generally it's that you're approaching that line, and here you're getting closer and closer to it. You're getting closer and closer to the vertical line, x equal 8. But you don't necessarily achieve it. Think of it as a guideline. Here are your horizontal asymptotes. If we extended this function out here, it would get closer and closer to the x-axis, closer and closer to the value y equals 0, but it wouldn't necessarily hit it. And here you can see the same thing over here. Okay, horizontal asymptotes are values of y. Y equals 0. Okay, here's this horizontal asymptote listed as y equals 0. The vertical asymptotes are x equals something. X equals 8, x equals 0, and x equals minus 2. A little summary of the analysis of polynomials. We look for y-axis intercepts. That means we set x equal to 0 When you set x equal to 0, you find out where the curve will cross the y-axis, whether it's a linear or polynomial or any function. Actually, set x equal to 0 and see what you get. That's where it will cross the y-axis. We look for turning points. Those would be your so-called peaks and valleys. A couple chapters will develop other terminology for them. That will be local maxima and minima. You can call them turning points. And then we have the x-axis intercepts, or the roots, sometimes called the zeros. Roots are the values of x for which the polynomial is 0. Of course, there can be distinct real roots. There can be equal roots, but they will have a multiplicity. And sometimes there's complex conjugates, although not in this class. The significance of complex conjugates in terms of graphing is that you can't graph them on the xy plane. Here's a very practical example of a polynomial. This will occur often. I'm looking for the time variation of the height of an object that is either thrown or dropped, or for example maybe shot from a cannon, and the path in the most simplest way to look at it is a polynomial. I like to use the following notation. I like y to be the height of the object above the surface of the earth, or whatever planet you're on. T, of course, is time. Y sub 0 is the height at t of 0. This is the initial value. Initial values are often written with a little sub-zero on them. V, which actually should have a 0 on it, is the initial velocity that's imparted to the object. If you simply drop the object and everything else is stationary, then that would be 0. If you shoot it from a cannon, then that is the velocity that it has when it leaves the cannon. And A is acceleration due to gravity. Okay. When this is assembled, you get a quadratic equation. Here, y of t, meaning the height as a function of t, equals y0, which is the initial height of the object, plus v times t minus acceleration over 2 times t squared. In this class, you will finally learn why acceleration is divided by 2 in this equation. What are the coefficients here? This is a constant term. Okay. Here is the first order term. Its coefficient is v. For the term that's squared, the coefficient is negative a over 2. The power function is both sort of a distillation and an extension of a monomial. In a power function, the coefficient is 1. So here's the power function right here. Its coefficient is 1. Okay? The exponent in monomial is a whole number. Here the exponent can be any real number. It could be 1/2, which you know is in square root. It could be minus 12. It could be minus 1.5. It doesn't matter. So this is the power function. And they're often studied separately. And in calculus, we do the calculations first. We develop the derivative. And we do the integral first for power functions. And then, using linearity, extend it to all polynomials. I'm going to show you some graphs of power functions. And this will be a first example of seeing families of curves. These are a bunch of curves that differ in one parameter. For the power functions, these graphs are going to fall into two categories, so I'll show you two different graphs. There's even functions, and those graphs are symmetric about the y-axis. Here, odd functions, they are symmetric about the origin. Okay. When you're looking at a family or looking at a group of curves, try first to find some values that are the same in all the curves. For example, all these curves go through the point 0, 0. Okay. Also, all the curves go through the point 1, 1. They're almost like stationary points, and things sort of revolve around those points. The even curves go through the point -1 and 1, and the odd curves go through the point -1 and -1. As the power is raised, you will see that the curves approach the axis, the x-axis, in the interval -1 to 1, that open interval there, because at -1 and 1, they always have the same value, and the curves become steeper when you're outside of that interval. Okay, so here's the power function graphs of the even powers. So the red line is x squared, the blue line is x to the 4th, and the green line is x to the 8th. They're all going through this point 0, 0 right here at the origin. They all go through the point 1, 1. They all go through the point -1 and 1. These are even functions. By even function means that if you find the value, you look at the function at some value of x, so you look right here. Oh, it's not making a line. There we go. And you look at the corresponding negative value of x. you see exactly the same thing in y. That's an even function. They're symmetric about this y-axis right here, which means one side is a mirror of the other side. Now look at this other behavior. If you're above 1 or below -1, then the curve with the highest value is x to the 8th, then x to the 4th, and then x squared. Same thing over here. But if you're between 1 and -1, that order is reversed. Now x squared is higher right here, x to the 4th, and then x to the 8th is closer to the axis. Some of us find things like that very amusing. What's happening here is that it starts out, x squared starts out like a bowl, and as you raise the power, it turns into a bucket. Okay. Let's look at the odd curves. Okay, here's the power function. These are graphs of the odd powers. The red line is x cubed, the blue line is x to the 5th, and the green line is x to the 9th. They all go through the same point. Always try to find points that everything's going through. In this case, 0, 0. Then they all go through the point 1, 1 right here, and they go through the point -1 and -1. These are odd functions. By odd, it means if you look at some value of x, for example, if I look right here, I look at the corresponding negative value of that x, I will see that the function has changed sign. If it was positive here, it'll have the same value here, although negative. That's an odd function. We say it's symmetric about the origin. If you put a thumbtack in the origin, you could revolve this whole figure. It's going to go like all over here. Whoops, that won't make an arrow for me. But at any rate, you would go and just revolve it about the origin. You would make the curve in the first quadrant turn into the curve in the third quadrant. Again, you have this issue of order. If you are greater than 1 or less than -1, the steepest curve here is the green one, which is x to the 9th, then x to the 5th, and then x cubed. Same over here. Now, if you look between 1 and -1, that order is reversed. I see the red curve, x squared on top, then x to the 5th, and then x to the 9th. If we combine power functions with different coefficients, we get these algebraic functions. Algebraic function could be a linear function, could be a polynomial, or it could be something like this. So we see a monomial, a coefficient of 12, x raised to a whole power of 3. Then we see another where the power is 1/4, which you know is the 4th root of x. And the last term, we have x cubed in the denominator. What is the domain of this function? We'll go through the same exercise that we did before. First, say it's all reals. Okay, fine. Then throw out any value of x that would cause you to divide by 0. Well, if you look at this function right here, x cannot be 0, otherwise you'd be dividing by 0. So x equal to 0 has just gone out of the domain. Then you look through it again, and you look through again, and you say, what are there any values of x that I would be taking a negative or an even root of? Well, here's x to the 1/4. That's an even root. So I cannot have x be any value less than 0. So we had a domain starting with all the real numbers. We threw out 0, and then we threw out everything less than 0. And here's the domain right here, written as it should be right after the function. X greater than 0.